Hello, today it's my pleasure to introduce you to linear systems. Linear systems of equations. These are equations that are linear in the unknown variables. For example, you could have an x, a y, but you wouldn't have an x squared or a y squared or an x times y in the equations. So we're going to do this. We're going to look at row reduction. We're going to graph the equations. We're going to look at matrix multiplication. We're going to solve it using matrices, and then we're going to finish with Cramer's rule. So let's look at a very simple two-variable example. So the idea here is we want to know the x and y variables that simultaneously satisfy both of these equations. What you could do is you could do a row reduction where you replace the A matrix with A divided by 2, and then you replace the B matrix with A minus B divided by 2. So this is what it would look like. To get A prime from A, it's pretty straightforward. You take A and divide by 2. So 2x divided by 2 is x. 3y divided by 2 is 1.5y. And 25 divided by 2 is 12.5. So that's pretty straightforward. To get the B prime, let's take a look. So what we could do is take the first equation, A, and then we could subtract off half of B. So you would have 2x minus 4x divided by 2. So that would actually eliminate x. It's 2x minus 2x. That would eliminate x, and you wouldn't even have an x. And then looking at y, you would have 3y minus 2.5 or 5 halves y. So that would be a half a y. And then if you had 25 minus 17.5, that's going to be 7.5. So that's how you can get a very simple equation there in B prime. And what that means is if you take B prime now and multiply it by 2, you actually get y equals 15. And that would be a B double prime, if you will, and just leave an A prime as it was. So now we actually know what y is that satisfies both equations at the same time. And then we can go and get x by using that first equation and substituting our known y and solving for x. And x is minus 10. So the solution then is x is minus 10 and y is 15. So we know the solution by, in this case, doing a row reduction. The second thing we can do is we can graph. In order to graph, we kind of want to do a slope-intercept form. So we want it to look like y equals something minus something times x. So that first thing is the y-intercept. So you get that by basically taking the original equations and then you put the 2x over on the other side. You take the 4x and you put that over on the other side, and then you divide through the first equation by 3 and the second equation by 5, and that's how you get the slope-intercept form. So this first part is the y-intercept, and the second part with the sign is the slope. So each one of these are negative slopes, so they should be decreasing when we plot it. So to plot it, what I did is I wrote a little MATLAB script here, and I'm plotting the two lines. So I get my x that I'm going to use in both of the lines, and then an x-array going from minus 15 to plus 15 in increments of 1. And then I get my y1 from the first equation, and then my y2 from the second equation that I've just generated for you. I'm going to plot the first one in a solid red and the second one in a green. So let's see what it looks like. There it is, and then you can see that x is minus 10 and y is 15. Okay, so let's talk about matrix multiply a little bit. So commutative, you remember back in your algebra days where you heard about this reflexive, associative, commutative, and you said, oh, this is so obvious, generally speaking. General things are commutative, but matrix multiplication is not commutative. Matrix A times B in general will not be equal to matrix B times A. They're not commutative. And the dimensions have to work out too. The number of left side columns has to equal the number of right side rows. So each row on the left side, let's take the first row of the left side, and the first column of the right, first row of the left, first column of the right, you dot those together, you're going to get A times E plus B times G, and that's going to be your first row, first column entry. So the number of rows on the right side is 2. That has to equal the number of columns on the left because you're dotting them together. So I usually think of taking my hand and putting it vertical for each column on the right, and then I rotate it and dot it with each row on the left. So let's do another one. Let's take a look at the first column and the second row. First column on the right, second row on the left. So that's going to be C times E plus D times G. So that's going to be second row, first column answer. Okay. Now, let's move on and do the first row on the left, second column on the right. So that's going to be A times F plus B times H. A times F plus B times H. So that's going to be first row and second column on the answer. And let's finish up with second row on the left, second column on the right. So that's going to be C times F plus D times H. Second row, second column. And that's how it works. And it carries through no matter what the dimensions are. So that's 2 by 2 times a 2 by 2 given a 2 by 2. So what if you had a 2 by 2 times a 2 by 1? Well, in that case, you're going to get a 2 by 1 answer. And you could see it's going to be the first one's going to be AB. It's going to be AB, row AB, times, you only got one column, EG. So it's A times E plus B times G. That's going to be your first one. And then C times E times D times G is going to be your second one. So that's easy. And you can't do this. So the sizing doesn't work out. If I were to try to take this column and dot it, I can't dot it with E. E's the first row because I got 2 things on the right and only have 1 on the left. So that doesn't work. So you don't do that. So I've seen students do that. I don't know what they're thinking. You can't do that. So that's matrix multiplication in a nutshell, is really just doing dot products of columns on the right with individual rows on the left. That's it. So let's think about matrix inverse. So when you multiply 2 matrices together and their result is the identity matrix. So identity matrix means that you've got ones along the diagonal, like we see here. That's a 2 by 2 identity matrix. So it's going to be square. So the matrix, to think of a matrix inverse, you have to be talking about a square matrix. And when you multiply 2 inverses together, you're going to get an identity matrix, which is ones along the diagonal. So let's do symbolically. Let's say that we've got a matrix A, B, C, D, and I'm trying to figure out what its inverse is. Well, I can tell you that it's going to be a scalar. You're going to have a scalar out here. We're going to talk about that in a second. 1 over capital delta. So we're going to have that on scaling the whole thing. And then how I remember it is for a 2x2, it goes like this. You take the main diagonals, you have A and D, and you switch them. So D and A, right? You switch them, and then you keep the anti-diagonal B and C. You keep those in the same place, but you just negate them. So it's a little bit of a trick here, but it's easy to remember what it is. And then delta, the delta here, the capital delta, is going to be A times D minus B times C. Okay, so let's think about kind of multiplying it out here and verifying what it is. So if I were to, just forget the 1 over delta for a second, forget that, and just take the D minus B and the minus C A, and when you multiply these together, you take that and dot it with that, you're going to get AD minus BC. If you take the first column and dot it with the second row, you're going to get CD minus DC, so you're going to end up with 0. And then it works out similarly for the other column when you do the minus B. When you dot the minus B and A with the 2 rows there, you're going to end up with a 0, and then again an AD minus BC. And then of course when you think about multiplying through by 1 over delta, where delta is that, you're going to get the identity matrix. So it is true that yes, verily, that is the inverse symbolically. Okay, so let's talk about a determinant now. So this is again for a square matrix, so same number of columns as rows. And we can talk about a determinant. So that's a scalar value, and you've got to remember that for a determinant, you end up with these vertical bars. It depends on the context, but here it's going to be A times D minus B times C. So it kind of works like this: A times D, and then you go on the anti-diagonal. You subtract the anti-diagonal, BC minus BC. So A times D minus BC, that's we call it capital delta, or the determinant. So just make sure that you understand the difference between the cornered brackets, which is a 2x2 matrix, and then the vertical straight bars here in the context of a determinant, which gives you that scalar. Okay, so let's see what we do. We want to rewrite these 2 linear equations in X and Y. We want to rewrite those in terms of a matrix form. So to me, these 2 look the same. Okay, so I've got the matrix 2, 3, 4, 5 as the left side, and then I have my unknowns X and Y, and then on the right side I've got 25 and 35 as a column. So X and Y is an unknown. It's a column matrix of unknowns, column vector of unknowns, and then I have my 2x2 is 2, 3, 4, 5. So what we want to think about here is what's the inverse of 2, 3, 4, 5. So if I know the inverse of 2, 3, 4, 5, then I can multiply both sides by that inverse, and then I'll have xy. Okay, so let's give that a shot. I'm going to multiply both sides by the inverse, which is just taking the 5 and the 2, swapping them, and then negating the anti-diagonal. And then as you can see, the determinant is minus 2. So I'm going to be multiplying that by the scalar minus 1/2, or 1 over delta, and I'm going to get the identity matrix over on the left hand side, And then on the right-hand side, I'm going to have 5 minus 3 minus 4 and 2, times that 25 and 35. And then, that's going to be pretty straightforward how that works out to be minus 10 and 15 again for x and y. So, we do, of course, get the same answer using the matrix inverse formulation. Well, matrix multiply and inverse. All right, so Cramer's rule is, let's say that you're given a linear system in matrix form, and what happens is Cramer's rule gives you the solution for x and y individually as ratios of determinants. And how it works is you take the matrix, the 2 by 2, and they're going to have a determinant always in the denominator, regardless of which variable you're solving for. So this 2 by 2 matrix is always in the denominator. The determinant of that that matrix goes there, and then what goes in the numerator is if you're solving for the first variable. Here we're solving for that x. So if we're solving for that, then I take that 2 by 2 and I replace the first column with the 25 and 35. So that's how I get that, and then I calculate this determinant, and then it's the ratio of the determinants that give me the value. And again, I get minus 10. So that's how it works for the first one. And then for the second one, I'm going to be talking about y. So I have the same denominator. It's the same 2 by 2 matrix over on the left-hand side. But then for the numerator, I'm going to take, since I'm looking for y, I'm going to take the second column and replace it with the 25, 35. So 25, 35 goes in the second column of the matrix, and then I go and calculate the determinant in the numerator. Same determinant in the denominator, but I end up with 15 when I'm done. So same results, right? So same solution. So we've looked at 3 different ways. We did a very straightforward 2 by 2 example. We did row reduction, we did matrix inversion, and then we did Cramer's rule on it. Okay, so we talk about accuracy here, and one of the homework problems actually challenges you to figure out which method is actually the most accurate. Okay, I hope you enjoyed it.